Alright, today we're going to have a look at topic 4, multivariable linear equations, part B. In our previous lesson, we have talked about how to solve a system of several linear equations, right? Specifically for the system that contains two linear equations. And today we're going to have a look at two shortcuts we can use to solve such a system. First one is called Cramer's rule, which is specifically applied to 2 by 2 case. I'll explain this later, okay? And the second method, we can solve a system of 3 or more linear equations, is called the matrix method. So these are the two shortcuts we can use to help us quickly solve a system of several linear equations. Okay, so let's have a look at an introductory example. We'll use this example to illustrate the concept here. Okay, suppose we want to solve the following system of linear equations. This system contains two linear equations, ax plus by equals e, and at the same time cx plus dy equals f, where ad minus bc is not 0. So how do we solve this? Usually, we need to reduce the number of unknown variables first, right? So we can multiply the first equation by d and multiply the second equation by b to set up eliminating the y terms, right? So we have from the original equation, we could have a new equation like this: a dx plus b dy equals de, right? And bcx plus b dy equals bf. Then we can use the we can just subtract the second equation from the first one, right? Which gives us ad minus bc times x equal to the right side is just de minus bf, right? And because it tells you ad minus bc is not 0, so we can divide both sides using ad minus bc. Therefore, we have x equals de minus bf over ad minus bc, right? And similarly, if you subtract the first equation from the second one, then you will have a similar result, which eliminate x there, which means ad minus bc y equals a f. First of all, we have to multiply them. We have to multiply our first original equation by c, which gives us a cx plus bcy equals ce, right? And multiply the second one using a. Therefore, we have a cx plus a dy equals af, right? Then we can subtract the first equation from the second one, which gives us ad minus bc y equals af minus ce. Therefore, we know y should equal af minus ce over ad minus bc, right? And therefore, we have a pair of solution like this, where x equals de minus bf over ad minus bc, whereas y equals af minus ce. The denominator is the same, which is ad minus bc, right? And in order for us to memorize this easily, in mathematics, we define a special operation which is called determinant. So a little background of the determinant. So a determinant is actually a special operation like this. Suppose we have four numbers, A11, A12, A21, and A22. The first number is the row number, and the second number denotes the column number. And this is actually a 2 by 2 case. A 2 by 2 matrix inside a pair of signs like this. So it looks like a absolute value, but it's not. And this is defined as A11 multiplied by A22 subtracted by A12 times A21. This is actually a special operation. For example, if you have a discriminant of 1, 2, 3, 4, then this will give you 1 by 4 minus 2 by 3, which is 4 minus 6, which gives you actually negative 2. So this is actually a number, right? And if we have a definition like this, then the solution can be expressed using the discriminant notation. So x equals, the denominator can be written as A, B, C, D, right? Because by definition, this discriminant gives you AD minus BC, which is exactly the same with this expression here, right? And the numerator can be written as E, B, F, D. And for y equals, discriminant is, denominator is the same, which is A, B, C, D. And the numerator is A, E, C, F. So why this is easily to memorize? Because if you check the denominator A, B, C, D is actually a matrix contains the coefficient of x and y, which is the A, B, C, D here, right? And for x, the numerator is, well, we keep the second row unchanged, second column unchanged, which is still B and D, but replace the first column with the constant numbers here, EF. So just put EF here instead of AC. You see that? And for y, again, this time we keep the first column unchanged, which is AC here, but replace the second column with E and F constants, not BD. Can you see that? Can you follow me?
Yeah.
Okay, so let's regulate the Cramer's rule for 2 by 2 case here. So the Cramer's rule for 2 by 2 case tells us that suppose A, B, C, D, E, and F are constants in the system of linear equations like this, ax plus by equals E, cx plus dy equals F. Cramer's rule states that if the determinant A, B, C, D is not 0, which means that actually equals AD minus BC, okay? If this determinant is not 0, then the solution to this system can be given as x equals the determinant of the denominator is the determinant of A, B, C, D, and numerator is E, B, F, D, where the second column are the same, but you change the first column using the coefficients, the constants here. So it's actually a ratio between two determinants. Did you get it? Determinant is actually a number. And y can be expressed as a fraction between two determinants. as well. Numerator, the denominator is the same with x, which is also the determinant of a, b, c, d. First row is a, b, second row is c, d. And the numerator now is, for y, for the second variable, you need to replace the second column using E and F instead of BD. You see that? You see the pattern here? So next time when you see this equation, you could use Cramer's rule to quickly find the solution. Alright, so I'll give you some time to write this down in your notebook, and next we'll have a look at an example, okay? Alright, I'll also put a note to help you understand. So note that this determinant A11, A12, A21, and A22 is defined as A11, A22 minus A12 times A21. It's actually a number, right? Okay, have you finished? If not, just let me know, okay? Otherwise, I'll just give you an example to illustrate how we can use Cramer's rule to quickly solve a system of linear equations like this. Okay, consider this question here. First, I'll give you 1 minute to try to solve this question using Cramer's rule, and then we're going to have a look at the solution together, okay? Okay, when you finish, you can put your answer into the chat box. That should be a pair of solutions then, right? There are two unknown variables, x and y. So what is x and what is y? You need to solve x and y, right? All right, let's have a look at the solution together. So basically, this is our A, right? According to Cramer's rule, this is our A, this is B, this is C, and this is D, right? And this is E, which is number, constant number. This is F, another constant number, right? And Cramer's rule said that if the determinant A, B, C, D is not 0, we can then use Cramer's rule, right? Now let's check if A, B, C, D is not 0 or not, is 0 or not. So A, B, C, D is just 2, -3, 5, and -2, right? Which gives us -4 minus -3 times 5, which is -4 plus 15, which gives us 11, right? Therefore, this determinant is not 0, so we can apply Cramer's rule to solve it. So we can directly write x is, in order to have x, you need to find this determinant as well. So for x, x is the first variable from left to right. Therefore, we need to replace the first column with the constant numbers, -5 and +4, right? Just keep the second column unchanged, which is -3 and -2. And this gives us -5 times -2 minus -3 times 4, right? And that's 10 plus 12, which is 22, right? And in order to have y, we need to calculate discriminant AECF, right? So that means because y is the second unknown variable, so we keep the first column unchanged, which is AC. So that's 2 and 5. Replace the second column with constant numbers, which is -5 here and 4 here, right? And this gives us 2 by 4 minus -5 times +5, which is 8 plus 25, which gives us 33, right? And therefore we know x equals the denominator is here, right? Which is determinant A, B, C, D, which is 11 here. And the numerator is this number, right? For y, the denominator is the same, which is 11, and numerator is here, this number, 33, right? Therefore, we know the solution is x equals 2 and y equals 3. Did you get it? Can you follow me? Jacob, Sunny, Ben?
Yes.
Okay, have a look at the solution here. And any questions, just let me know, okay? So next time when you see a problem like this, you can use Cramer's rule to quickly find the solutions. You don't have to use the elimination or the substitution method from the very beginning, right? Cramer's rule really provides us with a shortcut to find the solution for a 2x2 case. By 2x2, I mean the coefficients of x and y forms a 2x2 matrix. Alright, next let's have a look at the next key concept, which is to solve system of linear equations using matrix method. Again, let's use this example to illustrate the nature of this method. So let's consider this system of three linear equations: 3r plus 2a plus b equals 15, 5r plus 7a plus 2b equals 44, r plus 3a plus 5b equals 26. So basically we have three linear equations and three unknown variables, r, a, and b, right? Our task is to find the values of r, a, and b such that they can satisfy the three linear equations at the same time, right? So according to our previous discussion, we could either use elimination method or substitution method, right? So suppose let's use elimination method. So I'll copy the equation here, okay? Alright, so the three equations are 3r plus 2a plus b equals 15, right? Okay, second one, 5r plus 7a plus 2b equals 44. And then, let me check that. Okay, and then we have r plus 3a, then plus 5b equals 26. Alright, so let's make some equivalent transformation. By equivalent, I mean for each transformation, you cannot change the solution set. So the new system will have the same solution set with the previous step. Okay, so we're going to use elimination method, which means we want to eliminate or reduce the number of the unknown variables. So usually we'll put the smaller number in the first equation to facilitate our discussion. So let's move the third equation to the first position here. R plus 3a plus 5b equals 26. And then in the previous step, the first one becomes the second one in the second step, right? So 3r plus 2a plus b equals 15. And then 5r plus 7a plus 2b equals 44, right? So simply change the position of the equations. This does not change the solution set, right? And then we can use the first equation times -1, then add it to the second equation. Times -3 and add it to the second equation, right? This will eliminate r in the second equation. Can you see that? So the first one keeps unchanged, r plus 3a plus 5b equals 26. And first equation times -3 added to the second one gives us 0 here, right? And 3a times -3, which is -9, added to 2a, which gives us -7a, right? And then we have 5 times -3 is -15. So plus 1b gives us -14b, right? And -26 times -3 added to 15. This will give us -63, right? Can you follow me? Okay, let's align them a little bit. And again, we can also use the first equation multiplied by -5 and add it to the third equation. This will also eliminate the 5r here, right? So this will give us 0 here. And 3 times -5 plus 7a gives us -8a, right? And 1b times negative 5 added to 2b. This will give us negative, oh sorry, 5b times negative 5 added to 2b. This will give us negative 23b, right? And then 15 times negative 5 plus 44 gives us negative 86, right? Can you follow me? And again, this transformation does not change the solution set, but we have eliminated the two r's in the second and third equation, right? And then let's see if we can simplify any of the equations to help us facilitate the transformation in the future. So the first one apparently cannot be simplified. We'll just copy that. For the second one, apparently there is a common factor 7, right? So we can divide both sides using 7 or negative 7. If you divide it by negative 7, then that's better, right? So you will get each of the numbers positive. So we could divide it by negative 7. So 0 divided by negative 7 is still 0. Negative 7 divided by negative 7 is plus a. Then negative 14 divided by negative 7 gives us plus 2b, and equals, the right side is simply 9, right? And then for the third equation, we cannot do anything about it. So let's just copy that here. G equals negative 86, right? And then we can try to eliminate a in the third equation by using the second equation multiplied by positive 8 and add it to the third equation, right? And this will give us, okay, first one does not change anything. So let's just copy that here. And then second equation does not change. And let's copy it here. Then second equation times positive 8 added to the third one gives us 0 plus 0, right? 8a minus 8a gives us 0 here. Well, actually it's 0a, but it doesn't matter if you write a or not, right? And 2b times 8 minus 23b gives us negative 7b, right? And this is negative 14 here, because 8 by 9 is 72. 72 minus 86 is negative 14, right? And so far you have this. If you have a third equation like this, you can simply solve b is actually 2, right? So we can first simplify the third equation by multiply it or divide it using negative 7. So that's 0 plus 0 plus b equals 2, right? And then we can use the third equation times a negative 2, then add it to the second one. So this time third equation does not change. 0 plus b equals 2 times negative 2 added to the third one gives us 0 plus a plus 0 equals 5, right? And also we can then use the third equation times negative 5 and add it to the first one. Then that'll help us to eliminate b here, right? So that'll give you r plus 3a then plus 0 equals 16, right? Okay, and we can actually cancel the 3a here. How we can do that? So note that we can use the second equation times a factor negative 3 and add it to the first one here, right? And this will give us r plus 0 plus 0 equals 1, and 0 plus a plus 0 equals 5, and 0 plus 0 plus b equals 2, right? Can you follow me? If you have any questions, just interrupt me, okay? And therefore, in this system, you can easily solve that r equals 1, right? First one just gives you r equals 1. Second equation gives you a equals 5, and then b equals 2, right? Can you see that? So after a series of transformations, we finally have our final solution, which is r equals 1, and a equals 5, and b equals 2. And every transformation is equivalent. Therefore, this solution should be the solution of the original equation. Do you see it? Do you have any questions? And actually, for these transformations, what we are interested in most are the coefficients, right? So as you can see here, the order of r, a, and b does not change. So for each of the equations here, the first one is always r, second one is always a, third one is always b, right? All we care about is all the coefficients. So in the first system, we have 3, 2, 1, and 15, right? And then 5, 7, 2, and 44. Then for the third equation, we have 1, 3, 5, and 26. Then after the first step, we have 1, 3, 5, 26. Then 3, 2, 1, and 15, right? And then 5, 7, 2, 44. Okay, I'd better copy this first on this page. Sorry. Okay, I'll keep this page as a reference for you, then clone it. Okay, we'll highlight the coefficients in the cloned page. Okay, so we are interested in these coefficients together with the constants, right? So this is the original coefficients and the constants. So after one step transformation, we have 1, 3, 5, 26, then 3, r, 1, and 15, right? Then 5, 7, 2, and 44. Can you follow me? Then in the next step, we have 1, 3, 5, 26, 0 of r. Of course, doesn't matter you write r or not, right? So that's just 0. And -7, -14, and -63, and then 0, -8, -23, and -86, right? And then 1, 3, 5, 26, and then 0, 1, 2, and 9, then 0, -8, -23, and -86, right? And in the next step, we have 1, 3, 5, 26, then 0, 1, 2, 9, then 0, 0, -7, and -14. And in the next step, we have 1, 3, 5, 26, and then 0, 1, 2, 9, 0, 0, 1, 2. And then in the next step, we have 1, 3, 0, 16. 0, 1, 0, 5, 0, 0, 1, 2, right? In the last step, we have 1, 0, 0, 1, and 0, 1, 0, 5, and 0, 0, 1, 2. Also note that the three coefficients corresponds to the three variables in order, which is R, A, and B, right? R, A, and B, R, A, and B as well, for each of the system of three linear equations. So according to the last step, when you have a system like this, you can easily read the solution, which is R equals 1, A equals 5, and B equals 2, right? So as you can see here, all we care about are the coefficients together with the constants. So in the future, actually you don't have to write all of the equations. We can just write the coefficients of each equation together with the constants. So for example, we can just write the coefficients in order: 3, 2, 1, 15, and then 5, 7, 2, 44, right? Then 1, 3, 5, and 26. And do the transformations to these numbers. Actually, these numbers form a matrix. Therefore, this method is called a matrix method. And for example, from the first step to the second step, actually we can put the third row in the first row here, right? 1, 3, 5, 26. Then originally the first row becomes the second row: 3, 2, 1, 15. Then 5, 7, 2, 44. Again, you don't have to copy all the equations. We care about the coefficients and the constants only, right? So these coefficients are actually the coefficients of the original equations. And then in the next step, remember the first row does not change, so we'll just copy these numbers. The second row now becomes 0, -7, -14, and -63, right? Third row becomes 0, -8, -23, and -86, right? Can you follow me? Then in the next step, we can have the first row unchanged against 1, 3, 5, 26. Then the second row can be simplified to 0, 1, 2, and 9. And third row becomes 0. Third row does not change as well, right? Okay, then remember we can multiply the second row and add it to the third row. Then, of course, the first row does not change. Second row does not change. The third row becomes 0, 0, -7, and -14, right? And then in your next step, the third row can be simplified. Therefore, the other two rows does not change. But third row can be simplified to 0, 0, 1, 2, right? And then remember in the next step, we multiply the third row using number -2 and add it to the second row, right? So third row does not change. Second row becomes 0, 1, 0, 5. And we can also multiply the third row using number -5, and that cancels this number here, right? Therefore, the first row becomes 1, 3, 0, 16. And next, we can use the second row times a number -3 and add it to the first row. Remember that? So the first row becomes 1, 0, 0, 1. And second row is 0, 1, 0, 5. And third row becomes, third row does not change, which is 0, 0, 1, 2, right? And if you have a form of a matrix like this, then you can easily read the solution of the original equation, right? Because the order of the three variables does not change. So R is always here, A is always here, B is always here. Therefore, we have R equals 1, right? And A equals 5 and B equals 2. Can you see that? So this is our last step, because you can already find the solution. Therefore, we have r equals 1, a equals 5, and b equals 2. So the right side is actually called the matrix method. So in nature, you don't have to write all of the equations because we only care about the coefficients and the constant numbers. Can you follow me? Jacob, Sunny, Ben, can you follow me?
Yeah.
Do you have any questions?
Yeah.
All right. So do you need more time on this example? All right. So let's try to regulate this example in a more formal way, okay? So first of all, what is a matrix? Matrix is a rectangular array of terms called elements. The rows and columns of numbers are enclosed in square brackets like this, okay? Be careful with the difference between a matrix and the determinant we have just learned. So this determinant on the right is actually a number, but a matrix is actually a rectangular array of terms. It's not a number, but several elements inside it. So matrices are used to represent a system of linear equations without using variables. The coefficients of the variables in this system can be written as coefficient matrix. So if we only extract the coefficients, which are these numbers here, this number can form a matrix on the right like this. And this system also can be written as a augmented matrix, which we added another column, which are actually the constant number on the right of each equation. You see that? So each horizontal row of the matrix represents the coefficients from a single equation. The vertical line, well, not necessarily separates the coefficients from the constant term. So, well, you don't have to write this line here, okay? The positions of the rows are not important. They can be interchanged. The positions of the columns are important though, because that corresponds to the three variables x, y, z in order, right? They're always written in the same order. You see that? Do you have any questions? And based on the augmented matrix, we can do a series of transformations that can help us to solve this system. Okay, so now let's have a look at this practice. Can you write this system in the matrix form? A. And for B, if you are given a matrix form of system of linear equations, can you write the scalar equations that corresponds to this matrix? Okay, I'll give you 2 minutes to think about this question by yourself, and then we'll have a look at the solution together. Okay, so first of all, you should be able to convert the matrix form and the scalar form equations by yourself first. Okay, make sure you are able to do this. All right, have you finished? Let's have a look at the first one. If you have a system of equations like this, the matrix form of this equation is, well, we only extract the coefficient of each variables together with the constants on the last column, right? So the matrix form of this system is -3, 2, -5, and 6, then 4, -7. There is no z here, so that's actually 0z, right? So we'll put a 0 here, and 8 is constant. And for the last one, there is no x, so that's actually 0 times x, right? That's 0, -4, and 1, and 10. Did you get it? Can you follow me? Of course, you don't have to write this line here, because usually the last column is the constant numbers on the right of each equation. And for the second one, you can choose the names of the variables you like. For example, if you choose x, y, and z, then this matrix form corresponds to a system of 3 linear equations, which is 2x plus 0y plus 3z equals 1, and then -6x plus 11y minus 1z equals 12, and then 1x minus 8y plus 0z equals -3, right? Of course, you don't have to write 1 here. Of course, you don't have to write 0y here, right? You get it? Do you have any questions? Okay, so this is the first step. We use matrix form to solve a system of linear equations. And next, we're going to talk about what kind of operations can you perform on the matrix. These operations are called elementary row operations on matrix. Remember that these operations actually corresponds to the operations you performed on these linear equations on the left side, right? So for each transformation or operation, you can't change the solution set. So each transformation or operation must be equivalent transformation. So you can only do elementary row operations, which is defined as the operations you can do such that you do not change the solution set of the original system of equations. So elementary row operations can be performed on a matrix. These operations correspond to the actions taken when solving a system of equations by elimination. Elementary row operations change the appearance of a matrix, but do not change the solution set to the corresponding system of equations. These operations contains only the following 3 types of operations. First, any row can be multiplied or divided by a non-zero scalar value. This does not change the solution set. Second, any 2 rows can be exchanged with each other. This is equivalent to change the position of each equation, right? Of course, this does not change solution set as well. Third, a row can be replaced by the sum of that row and a multiple of another row. Again, this does not change the solution set either, right? So please remember that these are the only operations you can do on the equivalent matrix form of that system. Okay, please write this down on your notebook. Okay, I'll give you 2 minutes to write this down in your notebook. Okay, and we're going to have a look at some examples after this. All right, have you finished? Okay, so we have just talked about what kind of operations you can do on the matrix. And now let's talk about what is your target. After a series of transformations, our target is to transform the original matrix, such as the example here, into a matrix like this: 1, 0, 0, some number, followed by 0, 1, 0, followed by some number, and then 0, 0, some number, right? And if you have a matrix like this, then you can directly read the solutions, right? First variable equals this number here, second variable equals this number here, third variable equals this number here, right? So that's our target. And there is a special name for this type of matrix. This is called row reduced echelon form, or RREF. So a matrix can be changed from its original form into RREF by performing a series of elementary row operations. This row reduction process allows the solution to be read directly from the reduced matrix. So let's have a look at the RREF in detail. In RREF, the first non-zero element is in a row is a 1 and is called a leading one. And each leading one is strictly to the right of the leading one in any preceding row. In a column that contains a leading one, all other elements are zeros. Can you see that? And any row containing any zeros appears last. So for example, you might have a RREF like this: 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, and 0, 0, 0, 0. This is also possible. Okay, we'll talk about this case in some examples later. Okay, but normally, if you have a unique set of solution, you will have the ones on the diagonals here, and all other elements are just zeros. Then you can directly read the solutions. First variable is 3 in this case, second variable equals 2, and third variable equals -2, right? You see that? Can you follow me? Okay, I'll give you some time to write this down. Remember, this is our target, okay? After a series of elementary row operations, your target is to convert the original matrix into a RREF like this. Alright, have we finished? So let's have a look at an example. So suppose we have a system of linear equations like this. Can you use matrix method to solve a system like this? Okay, first of all, let's write this matrix form of this system. Remember, we only extract all the coefficients and the constant. Okay, first of all, you have to write these equations in the standard form, which means all the variables on left side and all the constants are on the right side. Then we can extract the coefficients together with the constant numbers only. So first equation corresponds to the first row, which is 1, 3, -1, and -9, right? And second equation corresponds to the second row, which is 1, -1, 1, 11, right? And third equation corresponds to the third row, which is 1, 2, 4, and 5. Then remember, our target is to convert this matrix to a form like this: 1, 0, 0, some numbers, 0, 1, 0, some numbers, 0, 0, 1, some numbers, right? And the only way you can do the transformations or do the operations are these three operations. Any row can be multiplied or divided by a non-zero scalar value. Any two rows can be exchanged with each other, and a row can be replaced by the sum of that row and a multiple of another row. Okay, so let's have a look at how we can do this. I'll put the target somewhere here, okay? Remember, this is our target. Okay, first of all, as I said, usually we'll put the smallest number, put the row contains the first smaller number in the first position. But in this case, because they are always 1, so we don't have to change the order of the equations. And usually we'll cancel these two numbers first. So we can use the first row times -1 and add it to the second row. So first row does not change, which is still 1, 3, -1, -9, right? But the second row, after the transformation, it becomes 0 here. 3 times -1 is -3. Added to the third row, added to the second row gives you -4 here, right? And then this number becomes 2. Then -9 times -1 is 9. 9 plus 11 is 20. Then we can also use the first row times -1 added to the third row, and third row becomes 0, -1, and 5, then negative and positive 14, right? And usually we'll cancel this number here by multiply the second row using a factor number. So in this case, we should multiply the second row using -1/4 and add it to the third row, right? But in that case, we'll introduce some fractions. Usually we don't like fractions because it will complicate the problem. So usually, again, we should put the row that contains smaller number into the second position. So let's switch the position of third and second row. So first row does not change, which is still here. Then switch these two rows. Okay, then next we can then use a second row here times a -4 and add it to the third row, right? Add it to the third row here. And this will give us, okay, I need to save some space. The first row does not change, still 1, 3, -1, -9. The second row does not change, which is still 0, -1, 5, 14, And then the third row becomes 0, 0, then 5 by negative 4 is negative 20. Added to the third row gives us negative 18, right? Oh, actually, before we do this, we can first simplify the third row, right? If we simplify that by divide it using number 2, that'll give us negative 2 here, and 1 here, and 10 here, right? Okay, and remember we want to convert this number to 1, right? Because this is our target. So let's multiply the second row using negative 1. So this gives us positive 1 here, negative 5 here, and negative 14 here. You follow me? Then we can start from there. So if you have a equation, a matrix like this, then you can use the second row multiplied by a number positive 2 added to the third row, right? So second row is 0, 1, negative 5, negative 14. Add to, times a positive 2 added to the third row becomes 0, 0, negative 9, and negative 18, right? And of course, you can then divide the third row using negative 9, right? That becomes 1, 3, negative 1, negative 9, 0, 1, negative 5, negative 14, 0, 0, 1, 2, right? You follow me? Then remember we want this number be 0 here, right? So we can use the third row times positive 5 added to the second row. You see that? So in this case, third row does not change, which is 0, 0, 1, 2 times positive 5 added to the second row gives us 0, 1, 0, and negative 4, right? We also want this number to be 0 here, right? Therefore, you can use this row times 1 added to the first row. This will give us 1, 3, 0, negative 7, right? Can you follow me? And also note that we want to cancel this number here. So we can use the second row times negative 3 and add it to the first row, right? And this will give us, okay, the last row does not change. This row does not change. And the second row times negative 3 added to the first row give us 1, 0, 0, negative 4 by negative 3 is 12, 12 minus 7 is 5, right? Can you follow me? And therefore, this is already our target, right? 1, 0, 0, 0, 1, 0, 0, 0, 1. That corresponds to x, y, and z, right? Therefore, we have the solution. X is 5, y is negative 4, and z is 2, right? You follow me? Now, do you have any questions? Jacob? Any questions? Sunny? How about Ben?
No.
All right, I'll give you 1 minute to have a look at the solution here, okay? And after that, we'll have a look at some special cases. All right, if you don't have any questions, let's have a look at some special cases. Actually, if you have a linear system like this, a linear system can also have no solution or unlimited number of solutions. For example, let's have a look at these two examples. First, okay, I'll just lead you through these examples, okay? Again, let's use matrix method to solve the first example here. Again, first, let's write the matrix form of this system, which is 1, -1, -2, and 5. Then second row is just 2, 2, 1, 1, right? Third row is 1, 3, 3, 10. Again, let's use matrix method to solve this equation. So first of all, we need to cancel these two numbers. We want them to be 0, right? So first of all, we could use the first row times the -1 added to the second row, right? And this will give us 1, -1, -2, and 5. And second row becomes 0, 4, 5, and -9, right? And then using the first row times negative, oh sorry, I made a mistake here. This should be -2 times -2 added to the second row. Then the second row becomes 0, 4, 5, -9, right? And then in order for this number be 0, we need to use the first row times a -1 added to the third row, right? And this will give us, the third row becomes 0, 4, 5, 5, right? Then remember, we also want this number be 1 and cancel this number here, right? So we could use the third row times a -1 added to the second row, right? So the first row does not change. The third row does not, I think it's better to use the second row times -1 added to the third row. So that second row times -1 added to the third row. Second one does not change. 0, 4, 5, -9. But the third row just becomes 0, 0, 0, and 14, right? So when you have a row like this, coefficients are all zeros, which corresponds to an equation like 0x plus 0y plus 0z equals 14, right? So basically you have equation 0 equals 14. Is this possible? Of course, no matter what x and y and z is, this equation cannot be true, right? Therefore, we know there must be no solution to the original system. Can you see that? So we can conclude no solution. Okay, you see why? Jacob?
Yes.
How about Sunny? Ben?
Yeah.
Alright, so basically you have 0 equals 14, and this is not possible for any pair of x, y, z. So we can conclude there is no solution. Alright? Okay, so have a look at the problem here. This is a special case. Sometimes this is possible, okay? Sometimes we do not have any solutions to a system of several linear equations. Alright, if you don't have any questions, let's have a look at the last example. And this example illustrates that sometimes we might have unlimited number of solutions as well. Okay, again, let's use matrix method to solve it. The corresponding matrix of this system is, okay, first row is 1, -1, -1, and -4, right? And 2, -1, sorry, 2, 0, because there is no y, so the coefficient of y is 0, right? So 2, 0, -1, and 3. And the last row is 1, -7, -4, and -37, right? So again, let's try to convert to RREF. And remember, we want to make this number be 0 and make this number be 0 first, right? So first of all, we can use the first row times -2 added to the second row, right? So the first row does not change. Second row becomes 0, and then 2, then 1, then 11, right? And then we can use the first row times -1 added to the third row. This third row that becomes 0, -6, and then -3, -33, right? Then apparently we can then simplify the third row by dividing it using -3, right? So if we divide the third row using -3, then we will get 0, 2, 1, and 11. So as you can see here, the second row are actually the same with the third row, right? So if we use the second row times -1 added to the third row, then the third row simply becomes 0, 0, 0, 0, right? The first row does not change. Second row does not change. But if we use the second row times a -1 added to the third row, this will give us 0, 0, 0, and 0, right? So basically that equation corresponds to 0 times x plus 0 times y plus 0, sorry, 0 times y, not z. 0 times x plus 0 times y plus 0 times z equals 0, right? We do know that there are unlimited solutions for this equation. And that equation is useless, right? So basically we only have two useful equations, but we have three unknown variables. If the number of unknown variables is more than the number of equations, usually you will have unlimited number of solutions. And how do we express these solutions? We can actually let y equals any number t, where t belongs to the real number set. Therefore, y could be any real number t, right? Then we have the second equation tells us 2t plus z equals 11, right? And this gives us z is simply 11 minus 2t. Again, t is a real number. Then if we put y and z into the first equation, we also have x minus y is t, then minus z is 11 minus 2t equals -4. And this tells us that x minus t minus 11 plus 2t equals -4. And we can solve. X is actually 7 minus t, right? Therefore, these are our solutions. well, y equals t is a real number, then z should equal 11 minus 2t, and x equals 7 minus t. So the solution is x is 7 minus t, y is t, and z, and correspondingly z equals 11 minus 2t, where t belongs to the real number set, which means it can be any real number, right? So t is actually a number that connects x, y, and z. As t could be any real number, x, y, and z can also be any real numbers, right? And their relationship can be represented by using the variable t here. So you can express your solution in this way. Did you get it? Okay, please spend some time on this equation. And any questions, just let me know, okay? All right, actually, after this class, you can also compare the solutions by using the matrix method and the traditional elimination method to see whether you will have the same set of solution, okay? And this is just a system that contains 3 linear equations. So the advantage of using the matrix method is not that obvious. But when you have a system of more than 3, for example 4, 5, or 6 linear equations, then the matrix method is very useful. So for example, if you have 1, 2, 3, 4 linear equations, the method should be the same. Then you will have a 4 by 4 equations, like 4 by 4 matrix, right? And if you add the constants as well, it's actually a 4-row, 5-column matrix. You can also use the same matrix method to solve that. This is usually quicker than the traditional elimination method. Can you see that? All right, do you have any questions?
No.
All right, so after this class, I'll give you some questions to practice, okay? So try to use the 2 methods we have learned in today's lesson to solve system of linear equations. And please remember to submit your solutions before the deadline. Well, preferably 1 day before the deadline, okay? 1 day before the next lesson. So I'll get the time to mark them and return them to you, okay? So if you don't have any questions, I'll see you next time. Bye.